Good evening, everyone, and welcome to the Amateur Radio General Class, session number 15. During our previous session, we tackled the following topics of critical angle, critical frequency, skip zone. We dealt with what scatter propagation is. We discussed NVIS. We also talked about what a notch filter is, the feature called attenuator, also noise blanker, noise reduction. We also discussed CW or Morse code operations. We talked a bit about how to do split operations or what it is, as well as dual VFO. We also discussed ALC. Then we talked about linear amplifiers and specifically tube amps. Then we went into what antenna tuners were. We discussed then some instruments such as the multimeter, the oscilloscope, antenna analyzer. We also discussed what a two-tone test was, and then we ended by talking about bypass capacitors and ferrite chokes. And we would have, of course, covered the question pool review for those items of theory that we would have discussed last session. Okay, so the agenda for this evening, we'll talk about how to do some interference reduction by grounding. Also, we'll be talking about ground loops and how to solve it by bonding. We'll discuss how to avoid RF burns and RF voltages from being in your shack. We'll also discuss a little more in depth what grounding and bonding is and differentiate between the two. We'll talk about electrical noise that's received on our amateur radio equipment. We'll also discuss a feature of transceivers called speech processors. We'll then discuss the S meter, and then we'll talk about what band edge and frequency ranges are. We'll also talk about mobile operations and the power supplies that we will use for it. And also specifically for mobile operations, we'll talk about the type of interference that we can get, sources of it. And then we'll also talk about some HF antenna systems for mobile. Then we'll go to solar cells, and then we will speak specifically of how solar cells are connected in series parallel. We will also talk about connecting solar panels to batteries and the use of the series diode. And then we'll also discuss connecting solar panels to lithium iron phosphate batteries and how we do that. And also we'll get into some operations such as SSB phone operations or voice. We'll also talk about the difference between USB or upper sideband and lower sideband when we use it. And then we'll get into some radio settings as well for phone operations. And we'll, of course, do our usual question pool review to cover all of the theory we would have gone through this evening. All right. So for persons who are joining us on YouTube, it seems as though every week we get quite a few additional persons that have a look at the sessions on YouTube, some for the first time. So if you're looking at this session live, this is the amateur radio training course, but we are doing level 2 at the moment, which is the general class. There's a level 1 course up on your screen at the links for the level 1, also known as the technician class course. So we have the links to all of the documents or handouts for it, as well as a playlist of videos that you can take that technician level. You're welcome to continue to view the general class, but just bear in mind we are in level 2 or the general class, and there's a level 1 called the technician class. All right. So in respect of our curriculum, up on your screen here, you can see that we are really progressing quite nicely. We are presently midway through amateur radio practices. We will actually finish that topic this evening, and we'll actually go on to operating procedures. So quite good progress indeed. And you realize after that, we just have 2 more topics, electrical and RF safety and commission rules, to bring this course to a close. So we are rapidly getting there. Just a reminder, please consider taking practice exams. It's never too early to take the practice exams. When you take the practice exams, it gives you an idea where you are with respect to your knowledge, and you may be quite surprised just how much you know already. And just bear in mind that the practice exams are taken from the same exact question pool that the real exam will come from. So it's really a good proxy. So if you're taking 3-4 of those exams and you're passing them, then it suggests that you may be very well ready to take the real exam. So it should build confidence as well. All right, this is just a slide that we continue to show for persons who would like to interact with the organization React, as well as to get some hands-on practice without actually operating on radio. It's an app called Zello. It's free. You can take a look at that slide on your own time. If you're now seeing it for the first time, you can spend some time going through what Zello is about, how to access Zello. Highly recommended you consider it, and of course you can interact with us on React. So relevant to this class or this course, we have material that has been distributed, including all of the slides in the slide deck that we do every week. The first link on your screen here, gdocs.tt React, you'll get all of the handouts as well as the slide deck. And the second link, gvids.ttreact.com, will take you to a playlist of all of the videos for this general class course. So if you have missed any or you want to review any, you can take a look at that link. Now remember, for these are actually quick links, so there's no S in HTTP, right? So it's HTTP, not HTTPS. So just bear that in mind if you're typing it in to your browser. It will just go and redirect you to the YouTube playlist. Okay, so for this course, we are using the No Nonsense General Class License Study Guide. So that's this highlighted in yellow. Feel free to avail yourself of the book either on the author's website or on Amazon. Please consider supporting the authors. There are also several other good books that we highly recommend that you consider getting, but it's really optional, but highly recommended. So you don't have to purchase anything to take this course, but it's always good to support the authors and also supplement your learning, looking through the different ways that various authors present information. You'll always learn something looking at it from a different perspective, and we highly encourage it as well. I don't believe we have any outstanding questions from last session. I think we took all of them live. So let's go straight into the material this evening. So sometimes as amateur radio operators, especially on the HF bands, we may get or encounter interference when we are operating our transmitter and receiver equipment. And grounding is one of those solutions that can help us to solve some of the interference and other negative side effects that we may encounter in amateur radio operating. Remember, we're using electricity to power equipment. We're using radio frequency to transmit. So with that, there are issues that can be solved or addressed properly using the concepts of grounding and also bonding. So we are saying that an amateur radio operator should use proper grounding techniques. And why we do that is to reduce interference. So we have a couple diagrams here, two of them here, that shows we have a radio, we have our power supply, we have maybe an accessory, it could be an antenna tuner, it could be an amplifier, and they may be connected to each other and go to the antenna. But notice that we are using some straps to go to a copper strip or a braid, and we are also grounding that copper strip or braid to ground, a ground rod that's outside into earth, right? So we do this to avoid what we call a ground loop. We connect all of them to a common point and then ground it. So let's look at these two, this diagram here, A and B. If we connect to a single point and to ground, this is what we are trying to achieve. But if we do something else that we should not be doing, this is not to do at the bottom here, just to illustrate. If we were to ground each item on its own, right? Notice the first diagram A here shows all of the items coming to a common point and then one ground. If we were to do something like this, where this is our radio, we ground it separately, we take our power supply, we ground it separately, maybe this is an SWR meter, we ground it separately, and maybe the amplifier that's in line and we ground it separately. What could happen is we can set up what we call a ground loop, right? And that ground loop could manifest itself on our receiver as a hum. You hear something like that on your radio and you're wondering what's causing that. That's because you may have a ground loop, right? So to avoid the ground loop, what we do, we take all of our equipment and we use a strap and connect it to one common point, and that common point is what we send to ground. We don't individually ground each piece of equipment to its own ground rod, right? We actually bond everything together and use one ground strap to go to the ground rod that's outside in the earth. So we have a couple of points here that are exam questions. The first one is that all ground conductors should be connected to a single point to avoid a ground loop. And that's the point that we make here, all connected to a single point. And this is the ground loop here that we are talking about, we're trying to avoid. We are not grounding individually the item to a ground rod by itself. We are going to one point and we're grounding that, because if we have separate grounds, these are the ground loops that could be set up there, and you will hear a hum as a result of that circulation. Also, another exam question, a possible symptom of a ground loop, which is this, is that in your station audio connection, you can receive reports of hum on your station transmitted signal. So you may be, your receiver may hear hum, and also if you are transmitting, the other amateur radio operator will say, you know, you're sounding okay, but there's a slight hum in your transmission. It could be a loud hum maybe. That hum could be generated in your audio circuitry due to ground loops. So that is why grounding, or proper grounding really, it's not just grounding, but proper grounding of your amateur radio station is important. And we have a few slides that talks about grounding, and you'll see these diagrams repeated over from a slightly different perspective, but the point is that we need to ground our equipment. All right, so, and by the way, there's a difference between an electrical ground and a radio frequency ground, so just bear that in mind, and grounding and bonding are very important to amateur radio. Right, so we did talk about ground loops, and this is an exam question which says that the effects of ground loops can be minimized by bonding all equipment enclosures together. So if you have a radio, it has an equipment enclosure, that's the box essentially, the chassis and the outside, that box, that enclosure. Power supply will have an enclosure, it's usually metallic, and we may have accessories, and those could be things like SWR meters, amplifiers, and other things that we put in line between our radio and our antenna. And we need to bond them together. So we kind of sometimes have a copper strip like this, and then we use straps to connect each item to ground them all together. And then, of course, to bond them all together, and then we use a ground strap to go to the ground rod. So this is an exam question. The effects of ground loops can be minimized by bonding all equipment enclosures together. That's what we're doing here, bonding it all together. All right. Okay, so again, we're repeating these diagrams to show how we connect or interconnect our equipment using these ground straps. So we need to be aware that there's also a safety component as well for why we ground. It could be that there are either voltages or radio frequency present in our shack or in our radio room if we do not ground and bond appropriately. So one of the exam questions here is that if improper grounding is used, meaning that we do not ground properly, an effect could be that a resonant ground connection, high RF voltages on the enclosures of equipment may result. So on the equipment, you could actually touch the equipment and you can get quote unquote a shock, right? Or the other bullet point is that you may get a burn, or what we call an RF burn, and that's not nice, that's quite nasty. So grounding and bonding will assist in removing that issue or reducing it significantly to the point where you are safer than if you did not, right? So grounding is important. We have another exam question here as well. A possible cause of high voltages that produce RF burns, right? So if you touch this radio and you get an RF burn, it could be because this ground wire here has a high impedance on the frequency that you're using. So the idea here is that this ground strap that goes from your this common ground copper strip to the ground rod. This strap here, we need to make it short, we need to make sure it's a heavy gauge, and we need to make sure it does not present a high impedance for the frequency that you're operating. Otherwise, what you can get is an RF burn. So that's an exam question, is that the ground wire has a high impedance on that frequency due to it being too long. So you want to keep it as short as possible, and these are two exam questions related to grounding and proper bonding of the equipment and how to be safe and to avoid getting a nasty burn or a shock even by touching your radio equipment. And folks, talk to any amateur radio operator that has not properly grounded the equipment. At some point in time, they would have touched a piece of equipment and they will tell you, you know, they got a little shock. Hopefully not fatal, but it's, you know, you can get a pretty bad jolt when you touch your equipment and you get that shock or that burn. So it's not nice, and you're being educated here about what you can do. So we expect as you become a licensed amateur radio operator and you purchase your equipment, you build your shack or radio shack, and you have your desk and you put your equipment laid out nicely, that you don't just connect the radio to the power supply and to your tuner and to the SWR meter and to the antenna, but you also take the time to bond the equipment together to a nice copper strap, maybe onto your wall, use that braid to bond them together, and then you will use another heavy gauge wire to go to a ground rod that's in the earth, right? So you're grounding and you're bonding as a trained amateur radio operator should. Okay, we're still on grounding and bonding. So again, most of our equipment tends to have metallic enclosures, right, for quite a few reasons as well. But we need to make sure that we need to ground all of our equipment to avoid hazardous voltages from being present on any of these chassis, right? So you don't want a hazardous voltage to be on your radio or your power supply or any accessory such as an SWR meter or an amplifier, for example, a tube amp or even a solid state amplifier. So what you do is you make sure they're all grounded, because if you don't, as mentioned before, that could be a safety concern. And this exam question here, this bullet point says that the metal enclosure of every item of station equipment, bar none, right, must be grounded to ensure what? That the hazardous voltages cannot appear on the chassis. Because if a hazardous voltage appears on the chassis and it's not properly grounded, you might be the ground. You might touch the radio and you become the ground. The current will flow through you. And there you go. You could get a pretty nasty shock as well, right? You could get burnt. So safety first. Also, another bullet point, it's an exam question. It says that a technique that helps to minimize radio frequency hotspots, that means RF hotspots on your equipment in an amateur station, is bonding all equipment enclosures together. So you don't want any of them to be isolated, your radio from the amplifier, from the power supply. You want to bond all of them together to bring them all to the same potential, and then when they're bonded, it's also grounded so that that safely shunts anything that may occur here to ground, so that you don't become that conductor or that conduit for that stray RF or that stray voltage to be conducted to earth, because you will be the ground rod if you do not do this proper grounding and bonding. All right, so these are all exam questions, very similar questions, they're all related. So, right, so let's talk about another issue as amateur radio operators that we encounter, and that is electrical noise. So on your screen here, we have, hopefully you can see it, there's an electrical pole and there's a transformer there. So sometimes, let's say if there's a poor connection on the transformer or one of these high voltage lines that's running, or medium voltage lines that's running here on the line, you can have what it was called arcing, right? If the connection is not properly made, you can have arcing, and arcing sounds like a buzzing sound, you know, bzz, 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 you know. You may have encountered it before. You're passing an electrical pole and there may be a transformer and you're hearing that arcing that's going on at the point of connection. Yes, excuse me. So that arcing can generate radio frequency noise. So you will hear it as an audio arc, but it's also that spark is really also going to be generating radio frequency transmissions. Yes. So we need to be aware, and this is an exam question, that electrical noise can often cause interference covering a wide range of frequencies on many bands, resulting from arcing at a poor electrical connection. So if there's a poor electrical connection somewhere along the way, that arcing or that sparking can create wideband noise. So if you look at your radio, you'll see maybe on 40 meters, 80 meters, 20 meters, you're seeing wideband noise, you know, and you're wondering what's causing all of that noise. And it could be that there's a poor electrical connection, in which case you call the electricity company and let them know that there's some arcing that's maybe going. Maybe you could see it, maybe you can see the sparking, or maybe you can hear it, and you can report it. It can also occur inside of your home as well, right? If there are poor electrical connections as well. But typically, it could potentially occur on the electricity supply lines as well. And that's why we have this diagram to show that it is possible to occur there as well. All right, so we have some extra information here. Not on the exam, but talking about use of digital signal processing, which can filter out some of those noises. Right? Extra information. All right, so let's just do probably a couple more slides before we take our break. All right, so one of the features on very good radio equipment transmitters is called a speech processor. What a speech processor does, it's very helpful to you to maximize and optimize your transmission. So when you're speaking to a microphone and that microphone is connected to your transmitter, you're expecting that voice using that phone mode to be transmitted across through the sky to the other amateur radio operator that is listening for your transmission. But again, if you speak too softly, then you will not have a good signal output, especially if you're using a mode such as single sideband, that the amount of power output is directly related to the voice input that you give the transceiver. So if you're speaking very softly, then you may not transmit as much power as you would transmit if you were to speak a little more loudly, right? So a speech processor can actually help you with those types of issues, right? To increase the loudness of your transmission. But remember, like everything else, too much of a good thing is good for nothing. So you don't want that speech processor to overly modulate or over-modulate your transmission either, because you'll have distortion resulting from it. So we have a couple, let's say, diagrams here showing you if you have an unprocessed speech. So this is just imagine that you're speaking and this is a waveform of your speech, right? Notice how it's pretty much low, you know. And if we turn on our speech processor, notice here that what was sort of a low waveform here, notice how the waveform is a bit higher, right? So the speech processor could increase the loudness of your voice as well. But at the same time, you don't want it to overly increase it, right? Because remember, we previously in the technician class and earlier in the general class, we talked about over-modulation and distortion if you drive your audio level too high. But you don't want it to be underdriven as well. So when you turn on your speech processor, if this is your natural voice here, and you turn on your speech processor and it boosts your voice here, notice the waveform is much higher. What that will also do is drive your transmitter more and cause your signal to be stronger that's leaving the transmitter, that's leaving your antenna. So what we say is that the average power is increased, right? So if you look here, the average power is lower than the average power here. You can see that the waveform is generally higher. So we say that the average power is higher, or we have increased the average power by virtue of increasing our voice levels. The transmitter will respond, especially in a mode such as single sideband. It will transmit a stronger signal from a stronger voice input into our transmitter. So let's deal with a couple of the exam questions in relation to speech processors. So first of all, a speech processor is very helpful, and you can find it in really good modern transceivers. You may not find it on all transceivers. Sometimes you need to have an external speech processor, but the point is that a speech processor is a very helpful feature. And exam questions, the purpose of a speech processor is to increase the apparent loudness. Remember we said, okay, this is our voice, maybe we're not that punchy. We turn on the speech processor, or we tune it up, or we turn it up, and we increase that level and loudness of our voice. So we go from this sort of fairly weak voice signal here to a stronger voice signal that goes into our transmitter. And therefore, the transmitted voice is increased. And it helps, especially during poor or bad band conditions where there's a lot of noise. The louder we are, the better we may be heard as well. But again, as we cautioned before, you don't want to be too loud because you can be distorted. We have another exam question here, which is that SSB phone signals. Remember, anytime in amateur radio we talk about phone, where it's really voice. So SSB voice signals are affected by increasing the average power of the transmission. So what that means, we have a average power that's fairly low here. Notice how the waveform is lower here. But because the waveform here is higher, commensurately higher, we're saying that the average power will also be higher because we have increased the average power of our voice level by turning on the speech processor. Another exam question, it will say, well, what happens if you incorrectly adjust the speech processor? Yes, remember we said too much of a good thing is good for nothing. So therefore, if we over adjust our speech processor and we drive our transmitters too much, we can get distorted speech, which is not a good thing at all. No one will understand us if we are distorted, or we'll have to repeat our transmissions, and that's not good, especially in an emergency situation. So you don't want to be distorted. You want to be just right. You want to be optimal. You want to be optimized. You don't want to be too low, and you don't want to be too high. You want to be just right. So one of the effects if you incorrectly adjust your speech processor is distorted speech. Also, you can generate what we call excess intermod or intermodulation products, which is also not good. That is multiple signals interlacing with one another, and you can get poor communication as a result of that intermod. And also, if you turn up your speech processor too much. So for example, I am talking right now to you, you're probably hearing a dog in the background. If I'm using a speech processor and I turn it up too much, that dog may all of a sudden overpower my own voice, right? So we say excessive background pickups could be one of those negative side effects if I incorrectly adjust my speech processor and it's too loud. It not only brings my voice to be distorted, but it brings other parasitic noises in the background. It will raise the level up, and then that also is not a good thing as well. So the exam question that you will get, they'll ask you, what are some of the effects if you incorrectly adjust your speech processor? The answer will be all of them will be correct, which is distorted speech, excess intermod or intermodulation products, and also excessive background pickups. These are not good things. So folks, I think now is a good time for us to probably take a short 2-minute break. Maybe just get up, take a little stretch, maybe a bathroom break, maybe have a little bit of water, and we'll see you back in approximately 2 minutes time. Okay, welcome back everyone. So Lundy is asking a question: can ground loops be created if multiple ham operators are in a small geographic area? So if you are in the same shack and you're connecting to common sources of electrical supply, for instance, or even antenna towers, yes. But if you mean by small geographic area, meaning one house to another house and so on, we would not normally talk about ground loops. What we may talk about, Lundy, might be more things like descents. Your RF, your radio frequency transmission could cause descents on other amateur radio operators' equipment. So we may recall we talked about selectivity and sensitivity. So those are probably more the effects in a geographical sense. But if the ham operators are within the same shack, the same room, certainly yes, it is possible, because it's usually the same electrical supply. You share common things, so yes, you can have it if it's within the same building or room or something like that. But if it's in a neighborhood you're referring to, not so much in the sense of ground loops, but you may be talking about descents as well as selectivity and sensitivity issues that may arise from that close proximity, especially if you're operating on the same general band itself or similar bands across. So excellent question there, Lundy. Okay, so let's continue our theory. All right, so we would have dealt with decibels during the technician class. We have talked a bit about it already in the general class. So we are now coming to a feature that is found on almost every amateur radio transceivers. I mean, commercial radios tend not to have these S meters, as we call them, but amateur radio operators, we tend to have the S meters. We tend to see what our transmission signal might look like, what our receive signal looks like, and so on, right? So commercial may not have it, but amateurs, we certainly are interested, and therefore we must be familiar with what an S meter is. So it's a gauge, and on your screen, hopefully we have a little screenshot that shows what it might look like, and you'll see some numbers, and they have some very specific numbers. So you'll see S here for S meter. You'll see 1, 3, 5, 7, 9, plus 20, plus 40, plus 60. So this is a decibel scale. So you'll notice it's not linear at all, right? You notice that for the same distance, we have gone from 9 to 20 to 40, 20 over 9, 40 over 9, 60 over 9. And from here to here is 1, 2, 3. So this is certainly not a linear scale, right? It's a logarithmic scale. It's a decibel scale. And we need to be aware of the S meter. We have some exam questions. And what an S meter measures for our purpose on a receiver is the strength of our signal that we are receiving. So if we receive an S1 signal, that's a fairly weak signal. If we receive an S3, well, it's still fairly weak, but it's stronger. Now, everything is relative here when we say weak and strong, right? So 5 is stronger, 7 is stronger, 9 is pretty strong, and then you have 20 over 9 or plus 20, right? And this is decibels we're talking about here, 9 dB or 9 decibel. Plus 20 over 9 dB, plus 40 over 9 dB, plus 60 over 9 dB, right? So this measures the receive signal strength, right? We have a receiver, and our incoming signals will be shown on this gauge here. So we've just shown a couple. This is S8, this is S9, and we have a couple points here that if we have a signal that was S8 and all of a sudden it's gone to S9, what that means, it's a 4 times increase in the signal. And similarly, if we have an S9 signal and let's say somebody and that operator turned on an amplifier and all of a sudden now that signal has gone to 20 over 9 or 20 dB over 9 or plus 20, that represents 100% power increase, right? So these are some exam questions that we have to deal with as well. So let's go with some of the bullet points, and these are exam questions. An S meter is a gauge that's found on most amateur radio transceiver receivers section, and it measures the received signal strength. So again, the higher that needle goes up, the stronger the received signal strength. The lower it is, the lower the received signal strength. So we also say that the scale is logarithmic, right? Remember, the decibel uses logs, right? And it log to base 10. So that an increase of 1 S unit is equivalent to a gain of 6 dB or 4 times. And we put up here a nice table here to, sort of remind us of when we talk about this decibel gain, what the power gain is. So if you remember, 3 dB gain is twice times, but a 6 dB gain is 4 times. So if you go 1 S unit up, 1 S unit is equivalent to 6 dB, right? So these are all exam questions here in the bullets. We also need to know that the power output of a transmitter must be raised approximately 4 times to change the S meter reading on a distant receiver from S8 to S9. In other words, we're going up by 1 S unit, but the power output of that transmitter must be increased 4 times. You need to amplify 4x or 4 times, and that's what we're showing here. If you have an S8 signal and you want to transmit, let's say you are transmitting and the far end, the person that's receiving, say, hey, I'm receiving you S8. If you want them to receive you at S9, all things being equal, you need to increase your power output by 4 times. So whatever wattage you're running, you need to multiply it by 4 to be able to effect an increase in that 1 S unit. So if you're going from S8 to S9, you need to multiply your power output by 4 times just to go from S8 to S9. So a lot of power just to go 1 S unit, right? Also another exam question. So this is an exam question here. Another exam question talks about going from S9 to plus 20 or 20 over S9, right? So if we're here, we're S9 and we want to achieve plus 20 over 9, we need to go with an output power of our transmitter 100 times. So if we are transmitting and the person says, yeah, I'm getting you at S9, and we want them to receive us as 20 over 9, we need to multiply our transmitter output power, or wattage, by 100 times. All right? So that alone tells you what this decibel signal is on the S meter. So this is an exam question here. A signal that reads 20 dB over S9 represents a signal that is 100 times stronger. And this is an exam question. So we have a little trusty table here that shows if we are 6 dB, it's 4 times, right? And that's S1. And if you want to go from S9 to 20 over 9, that is 100 times. All right. So exam questions. Right, so we have talked about single sideband before, right? And on your screen here, we have a little representation of what single sideband is. Remember, we have our carrier signal, and then when we modulate our signal in amplitude modulation, you have an upper sideband and a lower sideband that's generated. We also said for sideband operation, what we do is remove the carrier and one of the sidebands, and we are left with one sideband. So for example, we are left with the upper sideband. So this is just a little revision. If you have any doubts about that, you could kind of look back at the previous material. And similarly, for lower sideband, what we do is we get rid of the carrier and we get rid of the upper sideband, and we're just left with the lower sideband. So sideband operation is quite effective. But there are a couple of things that we need to know about sideband operations, right? So first of all, lower sideband, and we need to know actually any sideband occupies 3 kilohertz of bandwidth, right? So if you have a lower sideband signal, it occupies 3 kilohertz below the frequency that's displayed on your radio. So whatever the readout is on your LCD or on your display, the signal itself occupies a certain amount of bandwidth, right? And you need to know that it occupies up to 3 kilohertz below what is displayed. So even though you might have a specific frequency displayed, and we'll actually come to some examples in a little bit, right, to deal with actual numbers. Whatever that frequency is displayed, you need to be aware that if you are operating lower sideband, your bandwidth, remember, this is the frequency that's displayed here, the center frequency, but you're actually occupying bandwidth that's up to 3 kilohertz below that frequency, right? So you need to be aware. In other words, you are occupying space on a highway, on a lane, right? You're not just occupying a spot or one point, you are actually occupying a lane, and that is the bandwidth, right? So note that when you're transmitting, you are occupying bandwidth, right? And similarly, for an upper sideband signal, similarly, it occupies 3 kilohertz above the center frequency. So whatever you have on your radio display, if you say 7.169, if that's the frequency, you need to know that if you're operating upper sideband, your signal will occupy that frequency and also a bandwidth up to 3 kilohertz plus whatever you have displayed on your radio, which is the center frequency, right? So we have some exam questions. Let's deal with them. So when a 3 kilohertz wide lower sideband transmission, the phone segment, remember phone segment of the band is voice, the displayed carrier frequency, what that simply means is what you see on your radio, should be at least 3 kilohertz above the lower edge of the segment. So remember, in a band, you have a particular range of frequencies that you can use for voice. So in the case, for example, on this frequency band range, 7125 to 7.30, that's the valid voice part of the band. So if you're going to operate lower sideband, for example, here, you need to know that you cannot punch in 7.125 and go on lower sideband here because you will be outside of the band edge for voice, right? Remember, below that will be things like digital modes. So you have to go 7.125 plus 3 at the minimum. So that's what this bullet point is saying here. If you need to be aware of what is called the band edges. What are the valid frequencies as an amateur radio operator? You need to be familiar with your spectrum. You need to be familiar with the band plan, where you can operate digital mode, where you can operate phone mode or voice. You cannot just, willy-nilly. That's good, poor amateur radio practice. You need to observe the band plan. And if the band edge for voice or phone is 7.125, you cannot punch in 7.125 and then switch to lower sideband, because remember, if you put 7.125 here, then you're going to occupy 3 kilohertz below 7.125. So band edge, you need to be aware where the band edge is. And if you want to transmit the lower section of this band, you need to select 3 kilohertz above, right? And we'll actually give you the frequency here. So if you want to punch in, you want to use lower sideband on this band edge, you will actually have to set it to 7.178, right? So for 3 kilohertz lower sideband signal, when displayed the carrier frequency is 7.718, is 7175 to 7178. So what you need to be aware of, if you're punching in this frequency, it's occupying 3 kilohertz of bandwidth. So 7.175 to 7.178. If you subtract these two, you will get 3 kilohertz. So if you set your frequency to 7.178, which is this what's here, if you punch that frequency in, so what you're punching in here on your radio is 7.178. And if you're using lower sideband, your signal is going to occupy from 7.178 and less than that by 3 kilohertz all the way down to 7.175. So that's why you need to be aware of the band edge. You need to be aware of this band edge, for example, here, what the upper band edge is and what the lower band edge is. And make sure that when you select the mode, you don't go out of the band edge. That's one of the implications of these points. And similarly, as we talked about lower sideband, when we are occupying this piece of the spectrum here beyond the center frequency, if we are going to use upper sideband, we are going to occupy a spectrum that is above the readout frequency or the display frequency or the carrier frequency. So we need to take that into account as well. If our upper band edge is 7.300, for example, we cannot punch in 7.300 on our radio and then switch to upper sideband, because we will be transmitting from 7.300 to 7.305, which is outside of our band completely and outside of the band edge to begin with, and that is illegal operations. So we cannot go to the band edge and then select upper sideband at the upper end, right? So we need to always select a frequency on the display that when we select the mode, the bandwidth occupation does not go beyond our band edge. That's the point. So here's another exam question, bullet point. When using a 3 kilohertz wide USB in the phone segment, again, remember when we talk about the phone segment, we're talking about voice portion of the band. The display carrier frequency, that is what we display on our radio, should be at least 3 kilohertz below the upper edge of the segment. What they're saying here, let's say we're talking about this frequency band here, right? 7.300, we cannot punch that in. We need to go, let's say 7.297, right? That's the maximum that we can punch in here, and then go to upper sideband, and then we should not exceed. But you also don't want to push the envelope to exact, right? You want to be conservative and you want to go sufficiently, just in case you overmodulate or you drive your audio too much. You don't want to exceed that band edge, right? So you want to be conservative, and that's why you're training as an amateur radio operator, because if you were to transmit outside of the spectrum that you were allowed as an licensed amateur radio operator, that will be illegal operations. That's poor practice, and it's actually illegal. So specifically, the frequency range occupied by a 3 kilohertz USB signal when the displayed carrier frequency is set to 14.347 is 14.347 to 14.350. What does this mean? If we punch in on our radio 14.347, that's what our radio is displaying, and we select upper sideband, we need to be aware that the spectrum or the bandwidth that we occupy goes from 14.347, which is what is displayed on our radio, plus 3 kilohertz to 14.350. So we need to be aware of that. If we go anything above 14.347, our signal will go beyond the band edge, because we notice here the band edge is 14.350. And I will even avoid going to exactly 14.347, just in the off chance that I drive my audio too hard and it causes my signal to go beyond 14.350. So be very conservative when you're talking about using very close to the band edge. You need to be aware of how much spectrum your transmission is occupying. So if you're occupying upper sideband, apart from the carrier frequency, be aware that your signal, because when you apply your voice and you modulate, your signal is going to occupy a frequency that is higher than the display. And that's the point about these 2 points here. When you're doing lower sideband, it's occupying a frequency spectrum below what is displayed on the radio by 3 kilohertz. And if you're doing upper sideband, it's occupying frequency spectrum 3 kilohertz above what is displayed on your radio. So you need to be aware of that as a ham. You need to stay in your lane. You cannot drive on the grass, and you cannot you have to stay basically in whatever lane that you are, whatever your band edge is. You cannot go outside of it. You need to stay right in your lane. All right, so hopefully we have beaten that up pulp. So now we are coming to mobile operations. So mobile operations is when we install our radio in a vehicle, for example, right? And of course, you have different types of mobile operations. You can have maritime mobile, you can have aeronautical mobile. But typically, when we talk about mobile operations, we're talking about putting our radio in a vehicle, like a car, for instance, right? Or a truck or a van or something like that. And we need to be aware that when we put our radio equipment in our vehicle, we typically will try to power it using the vehicle's battery. So of course, we need to apply fuses and so on, right? But we also need to make sure that we use good cabling between the battery and our radio. We need to use sufficiently heavy gauge cables because this radio, for example, may be capable of outputting 100 watts of radio frequency power. And that's a fair amount of power it's going to draw from the battery. So the battery leads or the power cable needs to be of a sufficiently heavy gauge wire. Otherwise, you can have voltage drops, and also you need to put fuses as well, just in case you have a short circuit or in case you draw too much current. The fuses will protect your equipment, or protect the battery, protect your system, right? So that's the point of bullet point number 1. When performing an equipment installation, the best direct fuse power connection for a 100 watt HF mobile radio is to the battery using heavy gauge wire. So what they're saying here essentially is when you install your radio, you're actually going to install a cable to go straight to the battery. In other words, you're not going to go anywhere else, right? You're going straight to the battery, and quite often, sometimes that second connection is to the chassis as well, right? So just bear in mind, this is an exam question. The key points about it here: this is a 100 watt radio, you want to go straight to the battery using heavy gauge wire, and you are applying fuses to the power cable. So that's bullet point number 1. And bullet point number 2 is you might be tempted to use the accessory connector in your vehicle. Sometimes they call it a cigarette lighter adapter, or we have it on your screen here. You might be tempted to somehow connect your 100 watt HF radio to this connector. That's not a good idea at all. All right. The reason for that is that this cigarette lighter, I mean, yes, it may be sufficient to power some other pieces of equipment and even a cigarette lighter itself. But this is unlikely to be sufficient to sustain amateur radio use, especially if you have a 100 watt piece of equipment, right? So that's the bullet point number 2. They are advising against using this. It is best not to draw the DC power from a 100 watt for a 100 watt HF transceiver, that's your radio, from a vehicle's auxiliary power socket. Read this as auxiliary power socket, meaning cigarette lighter adapter, because the socket's wiring may be inadequate for the current being drawn by the transceiver. And I mean, these things could actually melt, right, if you draw too much power. And we have seen it happen already, right? Sometimes the plug that goes into this can melt as well, right? So try to avoid using it, especially with high powered equipment. If you're using QRP or low powered equipment, maybe you can get away with that, right? But it's always best for amateur radio operation to go straight to the battery. And that's what these points here are about. In mobile operations, the type of power supply that you will use for your radio. So you have your radio here, you have your battery. This firewall here is between the inside of your vehicle and where you have the engine and the battery compartment. You have your antenna connected to your radio. And of course, you may have other accessories such as a tuner and so on. Yeah? Okay, so we stick with mobile operations. We can have interference. There are a couple of sources of interference that we can encounter with our mobile radio operations, right? So especially if it's an HF radio, you can get all sorts of static and noises and snap, crackles, and pops. And we need to know about the various sources that can cause us that bit of heartache when we put our radio into our vehicle. So the first one is that the battery charging system. Remember, you will have to charge up the vehicle battery, that starting battery that will power your amateur radio equipment as well. That starting battery has to be charged up. And when that is charging, your battery is being charged, the electronics that are involved in charging the battery can generate interference or noise that will manifest itself as all sorts of interfering audio snap, crackles, and pops that you may hear on your when you're listening, when you're receiving, and also sometimes when you're transmitting. The other party could sometimes pick up that noise as well. So you need to be aware that's one of the sources of noise. Also, another source of noise, sometimes especially with electronic ignition, all of the electronics in your vehicle, those components as well in the fuel delivery system can also lead to some noises that will be heard when you are listening to a transmission, right? What we call receive interference. And last but not least, your what we call the brain box of the computer and the control system or the control computer that in most vehicles these days are electronic ignition, computer controlled. It's no longer the sort of carburetor type vehicles anymore. It's pretty much, and even electric vehicles as well, a lot of electronic controls. And those electronic controls have switching circuits. They have different types of circuits that will generate noise, broadband noise on the radio frequency spectrum. And sometimes they're not well filtered. So the vehicle control system, sometimes called, people commonly call it the brain box, that controls all of those sensors to optimize fuel, the vehicle operation. That computer that controls your vehicle, the circuitry associated with it can also be the source of noises when you are listening to transmission. So these are the three types or sources of interference when you go mobile operations, especially on HF. So let's deal with the exam question. An HF transceiver that's installed and operated in a vehicle is susceptible to noise from the vehicle's electronics, and that may cause receive interference due to the following: battery charging system, that's what we just discussed here, the fuel delivery system, that's what we just discussed in this diagram, and also the vehicle control computer, sometimes called the brain box, which is what we discussed in this diagram here as well. So the exam question will say, what are some of the sources of interference on your vehicle mounted HF transceiver? It will give you these three options, and the answer will be all are correct: battery charging system, fuel delivery system, and vehicle control computer. Right, we still have a couple more slides to go, folks. So also in mobile operations, well, we have our HF transceiver, for instance. We mount it in our vehicle, but we also need an antenna. So when we have our HF transceiver mounted on our base station, we may have an antenna like this, a full-size antenna. It's pretty long, maybe several feet tall. And this is our base station antenna. This is a vertical antenna. We may have other types of antennas, Yagis, and all sorts of elaborate design antennas, long wire antennas, dipoles, and so on. But we cannot put such a large antenna like this on our vehicle. So we have to have a compact version of an antenna when we're doing mobile HF installation. So yes, we can operate HF on our vehicle, and we may have a compact version of an antenna. And that tends to be a bit of a compromise. When we have a full-scale or full-size antenna closer to the wavelength of the frequency that we're going to operate, we'll have better efficiency, maximum signal transfer. But from the time we start to use a smaller antenna, yes, we'll use it, it'll be shorter, but we are giving something. There's no free lunch. So with that compact nature, we may end up being less efficient than a full-size base station antenna, right? So that is considered a bit of a limitation when we go mobile operation. So let's deal with bullet point number 1, which just kind of rehashes what we just said, which is operating an HF radio mobile installation. That means you put your HF radio inside of a vehicle of some sort, is a compromise. And one of the limits being poor efficiency of the electrically short antenna. Because you're shortening the antenna, maybe using a coil of some sort or some other mechanism to shorten the antenna, that is compromising the antenna's ability to transmit an optimal signal or very efficient signal, and we need to know that because the antenna length is short compared with the wavelength. So compared to a base station antenna, which will be physically longer, maybe at the length of or half wave, for example, of the antenna, the frequency that we're operating, when we go mobile, that antenna will not be as long and we may use a coil. So electrically, it will look good to the transmitter. The SWR will probably be relatively okay, but we are sacrificing efficiency and getting our signal out as well as we would otherwise on a base station. So it's a compromise going mobile. So there's another disadvantage as well. So when you have a base station antenna, you may have a good SWR across a range of frequencies. When you go mobile, compared to the full-size base station antennas, your operating bandwidth might be less. So some antennas, like these antennas, screwdriver antennas, you can adjust and, to suit, but you may certainly have to have a stronger antenna tuner inside of your mobile to cater for the fact that the mobile antenna's bandwidth may tend to be less. So let's deal with that bullet point. Another disadvantage of using a shortened mobile antenna, because it will be shorter, as opposed to a full-size antenna is like this one on your base station, which matches closer to the wavelength of operation, is that the operating bandwidth may be very limited. What that means is that once you go left or right of the tune frequency, you may find you have an SWR that is higher. So that's what we call the bandwidth of the antenna. For what range of frequencies the antenna will present a low SWR, right? Or will be resonant. 2 exam questions. Okay, let's continue again. We're still on mobile HF antenna systems. So when we look at mobile HF antennas, so this is an example of a mobile antenna, and you may see something looking like this on top of the antenna. And you may say, well, what is that? That is called a capacitance hat. And what that does is that it helps to electrically shorten the antenna. Rather, it makes it physically shorter, but it electrically lengthens it. So even though the antenna is shorter physically, electrically from a radio frequency standpoint, the radio will see the antennas looking longer. So this is called a capacitance hat, and that is one of the techniques. Also, a coil is another way to electrically lengthen but physically shorten an antenna. But a capacitance hat, for the purpose of this exam question, and this is what it might look like, will electrically lengthen the antenna beyond the physical length and make it physically shorter for mobile operations. So let's deal with that exam question. To electrically lengthen a physically short antenna, as in the case of mobile HF operation, a capacitance hat can be used. And we're showing visually here, making it real. This is what a capacitance hat might look like. So if you ever look at a mobile antenna and you see this, you will wonder what this crazy ball of wire looks like. What is it doing? It's called a capacitance hat, and it's doing, what it's doing is, while this antenna is shorter, it makes it electrically longer for the purpose of radio frequency, but it's a shorter antenna so that it could be vehicularly mounted. Right, so on some antennas, you may see something like this, a little ball, right? This is called a corona ball, and what that can help do is to discharge radio frequency voltage from a mobile antenna. So if you look at a mobile antenna whip, you may see something like this, or sometimes you'll just see the top of the antenna nicely rounded like that. But when you see this that's added on to the antenna, it's called a corona ball. So let's deal with that exam question. To reduce RF voltage, radio frequency voltage discharge from the tip of an HF mobile antenna while you are transmitting, a corona ball can be used to disperse the charge at the tip of the antenna, thereby decreasing the voltage. So this is called a corona ball, and this is an exam question. Right, so let's deal with some renewable energy items here. So we're going to deal with solar panels and solar cells. So most of us probably are aware of solar panels. There's a lot of it in the news. We're talking about going renewables, going green, and solar panels are one of the technologies that we see as when we want to go green. So as amateur radio operators as well, we can use it, and we do, especially for off-grid operation, emergency operations, emergency communications, or just to test our emergency capability. We may have solar panels, and solar panels consists of solar cells, right? And we say that as AHAMs, we tend to use them quite often off-grid. If we are operating, let's say, somewhere in an urban area. We could use electricity, yes, but we can also go off grid. If we are in a rural area, we can also do this. Maybe we don't have a line supply coming from the electricity company. So we can use solar panels to power our amateur radio equipment, right? And we encourage hams. One of the things you may want to do, apart from becoming a licensed amateur radio operator and acquiring your equipment, is your ability to have a go kit that you can go and operate if there's an emergency and there's no electricity around. So solar is one of the ways that you can do so. And what solar panels do, it converts the energy from the sun to an electrical source that we can use to power our equipment. And we need to be aware that a solar cell, there's a voltage that's generated in a solar cell, and the voltage is approximately 0.5 volts DC, right? So this is a solar cell on your screen here, and when the sun hits it, this is one cell, it will generate electromotive force, it will generate a voltage, and that potential difference is approximately 0.5 volts DC, and that's the exam question. The approximate open circuit voltage from a fully illuminated silicon photovoltaic cell is 0.5 volts. So illuminated means that the sun is shining in it. Silicon photovoltaic cell, well, that is the substrate that is used for constructing solar panels. We just need to know that that voltage that's generated by that cell is approximately half, or 0.5 volts DC, right? So again, direct current. Right, so we will have individual solar cells to make up a solar panel. And we need to be aware that those solar cells, individual cells, are connected in what is called series parallel. But what is series parallel? So we would have dealt with what series circuits are. That's DC chaining one into the next. And parallel, we also dealt with parallel circuits when we talked about resistors and capacitors and inductors. You may recall when we discussed parallel circuits, right? Where we have the concept of branching. But in the case of solar cells that we're connecting together to make a solar panel, we are connecting them in series parallel. So the individual panels like this will be in series. So you have these two solar cells, right? I mean, these are really solar panels on your screen, but think about this as a solar cell connected to another solar cell. These two are in series. But notice we have two others here that are also in series, and we have two others here that are also in series. But then we connect these sets of series connected solar cells in parallel. So that's what we mean by series parallel. It's a combination or hybrid. These two are connected series, these two are connected in series, these two are connected in series, right? They're daisy chain. But then we come now and parallel connect these arrays. So that's what we mean when we say that solar cells are connected in series parallel to make up a solar panel. And that's an exam question. Individual cells in a solar panel are connected together in series parallel configuration. All right. Okay, so I have a question here from David. Does lightning produce static noise that can harm radio devices? And if so, what precautions can we take? So David, that's an excellent question. And yes, certainly, ham radio operators need to be very conscious of lightning. And that is because we tend to put up amateur radio equipment, we tend to put up towers, we tend to put up poles, and we tend to mount our antennas on those high poles or towers, and we tend to become a lightning arrestor, right? We tend to be a lightning rod to attract lightning, right? So as hams, we can cause lightning to hit our station. So what we do, we protect it. We can use grounding as one. We can use polyphasers to make sure that if we are struck, that it will shunt the discharge to ground. But at the end of the day, if you have a direct lightning strike, lightning is so strong that even if you're grounded and using polyphasers, you can still get your equipment damaged, right? Lightning is just so strong. But if you have a side strike or a strike that is nearby, you might get away, by just grounding. Some hams, what they do when there's a lightning storm around, will disconnect the coax and put it outside the shack so that it doesn't come into the, connected to your equipment. You disconnect it. But grounding, you cannot always be home when there's a lightning storm around, right? So grounding and bonding is critical, and also using things like polyphasers that will essentially shunt that discharge to ground should it, similar to what you will have protecting your equipment in your house, where you have surge arresters that's comprised of metal oxide varistors or MOVs. It will shunt that spike or transient to ground. You have equipment that will do a similar thing for lighting. There's also devices, quite expensive, that you can install lightning rods around your location. There's also equipment that can create a bit of a blanket as well around your area, so that you are somewhat protected, right? So there are active devices that are sold commercially that can do that. So yes, excellent question, David. It is a significant concern. It can cause and does cause noise. A lot of electrical noise that you hear when you are listening to your amateur radio receiver is generated by lightning somewhere around the world. And there are sites that you can go on to see where there's lightning real time as well, real-time lightning strikes. And there are devices as well, also websites that can alert you when there's a lightning strike or there's lightning nearby. So very significant concern of amateur radio operators. You ground as best as you can. You can disconnect if you wish when it's nearby, and you can also invest in more expensive lightning protection, lightning rods, creating a blanket using those modern devices to protect your equipment. But again, lightning is such a serious and strong phenomenon that sometimes, even with the best of protection, if it's a direct strike that you're getting, sometimes there's not much you can do to prevent the damage, right? And many amateur radio operators have been had their shacks, their stations struck by lightning. So excellent question there, David. All right, so we took that question. Let's continue. Right. So staying with solar panels. So this is a solar panel here, for instance, and we have connected it to our battery to charge up our battery, and then our battery may be connected to our transceivers, right? So we need to be aware that if we have our solar panel connected to our battery, let's say in the nighttime, for instance, when the sun goes down, this solar panel is no longer able to deliver an electromotive force to the battery to charge it. So what may happen is that the battery may now start to send power now to the solar panel, right? So to avoid that, you put a diode, and you may recall what a diode does. It allows electrons to flow in one direction only, a regular diode. So that's what you do, is a sort of check valve operation. You put it in to avoid the battery from somehow trying to power the solar panel. That's not what you want to do, right? So that's an exam question. A series diode, which is this here, is connected between a solar panel and a storage battery. This is the storage panel. This is the storage battery here, and this is the solar panel here. This is the diode. It's connected. And this panel, of course, is charging this battery, charged by the panel to prevent discharge of the batteries through the panel during times of low or no illumination. So what that means is when the sun goes down, this panel is no longer able to charge the battery, and the battery, if you don't install this diode, could potentially try to send power back through the solar panel and discharge itself. So this diode here prevents that from happening. Again, like a check valve. Right, so again, we can use our solar panels to charge these relatively newer types of batteries. They tend to be very light, they tend to last very long. They're called lithium iron phosphate, or LiFePO4, right? That's a very popular type of battery now. They last much longer. They're much lighter, and hence they're quite popular. Of course, they're certainly a bit more expensive. And you can charge your lithium iron phosphate batteries via solar panels. So this is a solar panel here, and this is your lithium iron phosphate batteries, also called LiFePO4, right? Those modern batteries. But we need to know for the exam that you don't just go and connect your solar panel straight to your batteries, right? What you do is use what is called an MPPT, or a charge controller. And this charge controller will optimize the delivery of the power to charge your battery, especially if your battery is of the lithium iron phosphate type. I mean, you should use it generally for, I would say, any type of battery. You really should, right? You want to optimize that power delivery. So this is an exam question. It's a precaution that should be taken when connecting a solar panel. This here to a lithium iron phosphate battery, that's the battery here, lithium iron phosphate, is that the solar panel must have a charge controller, and this is our trusty charge controller here that sits between the solar panel and this battery, lithium iron phosphate. We just give you a little bit of extra information here, and we say this is to prevent overcharging, deep discharging, and also to generally optimize the charging process, thus ensuring battery safety and longevity. In other words, to make this battery last longer, you want to treat it right and make sure that it's charged properly, and the charge controller for this type of battery is what will help you do so. So a little extra slide here, quickly talking about wind power. You can read this on your own. Right. So that was the end of the amateur radio practices section. We'll just do a couple quick slides on the next topic, which is operating procedures, right? So phone operations, again, phone operations in amateur radio is when we speak, we use voice, and SSB is single sideband. So single sideband is actually one of the most common modes that is used in amateur radio, especially on HF, right? So HF amateur bands, the mode of phone operation or phone communication or voice operation that is most commonly used is single sideband, also known as SSB. So what is SSB? You may recall, you generate an amplitude modulated signal, you strip off the carrier and you strip off one of the sidebands. When you do an amplitude modulated signal, you have the two sidebands and you have the carrier. But you use filter circuits and you strip off the carrier, which is not needed. You strip off one of the sidebands, which is redundant, and you have the information carried on one of the sidebands. So this is called single sideband operation. We covered this in the technician class, so you can review that material if you want further information, but we're just quickly reviewing what SSB is. But just to note, there's an exam question that SSB is one of the most common modes on the HF bands when it comes to using voice communication. So this is an exam question. And we need to know that only one sideband is transmitted. The other sideband and the carrier are suppressed or filtered. So this is it here. We generate our amplitude modulated signal. We strip off or we suppress the carrier, and we strip off or we filter out one of the sidebands, and we end up with the other sideband. So if we strip off the lower sideband, we are left with only the upper sideband. If we strip off the upper sideband, we are left with only the lower sideband, right? So this is how, or what single sideband operation is about. Now, there's an advantage when we use SSB compared to the other analog voice modes on HF. And that is, one, it uses less bandwidth. So an amplitude modulated signal uses all of this bandwidth here. But if we take away one of the sidebands and we just left with one sideband, it uses much less bandwidth, right? You could see that visually here. And as a result of that, our transmitter, we can send more power using this piece of the spectrum only. So therefore, we have a greater efficiency as well, which is the last bullet point, I believe. Yes. So an advantage when using single sideband or SSB as compared to other analog voice modes, such as AM, for instance, on the HF amateur bands is less bandwidth for SSB, and greater power efficiency, because we don't have to transmit the carrier and we don't have to transmit or send any power to transmit the sideband or the carrier. We are just transmitting one of the sidebands, and therefore we could concentrate all our RF power on just transmitting that part of the sideband. Exam question. All right, a couple more slides before we go into our question pool. And again, folks, we're going a little over time again this evening. So upper sideband, so remember we said USB is upper sideband and we have LSB, which is lower sideband, but upper sideband is most commonly used for voice communication on frequencies greater than 14 megahertz. So we'll come to our last, one of our last slides where we have all of this compared and contrasted for you, but we need to know for the exam that USB is used above 14 megahertz, right? So 14 megahertz and above, we use upper sideband. That's a convention. So for example, the 17 meter band, which is 18 megahertz, and the 12 meter band, which is 24 megahertz, we use upper sideband. And these are two exam questions here in one. Upper sideband is used for frequencies of 14 megahertz or higher or above. And it's also 18 megahertz, which is 17 meters, 24 megahertz, which is 12 meters. This is another exam question we use upper sideband for. So upper sideband is also commonly used when we are doing single sideband on VHF and UHF. So anytime you're using single sideband or SSB and VHF and UHF, it is pretty much always upper sideband. We don't really use lower sideband when we're doing SSB on VHF and UHF, right? But on HF, we'll use upper sideband for 14 megahertz and above. And this last bullet point here is that we will use lower sideband for anything lower than that. So lower sideband is most commonly used for voice communications on the 160 meter, which is 1.8 megahertz, 75 meters, which is 4 megahertz, and 40 meters, which is 7 megahertz, right? Because it is commonly accepted amateur practice. So it's just a convention really, right? So we'll come to a slide where we show where upper sideband is used and where lower sideband is used. So this is an extra slide, folks, so you can read this on your own time. And our last slide before we go into the question pool questions is when we are making contact on amateur radio, we are calling someone, we are listening, we are speaking, that's radio operations. We want to have a conversation. We need to tune up our radio properly. We need to make some adjustments. And some of these adjustments are in the menu system of the radios. Some of them are using these knobs and dials to make different adjustments to optimize our signal. We want our signal to be loud and clear. So there are a couple of settings that we need to be aware of for the exam, and as an amateur radio operator in practice, we need to adjust these signals to tune them up appropriately so that our signal can be heard and received loud and clear. And that's the subject of one of these the second bullet point here is that the transmit audio or microphone gain control, and we have highlighted it here. It can also be a button, it can be a touch screen on the LCD. Microphone gain control is typically adjusted for proper automatic level control or ALC setting on an amateur single sideband transceiver. What this is trying to say here is when we are operating SSB, we need to make sure that our microphone gain is properly adjusted. You don't want it to be too low because, as we said before, if it's too low, then we will not drive our signal. As a matter of fact, we might want to use a speech processor to drive our signal even higher. And if we drive our signal, our audio signal too high because our microphone gain is set too high, we may cause distortion. So it needs to be just right so that the automatic level control will not attenuate our signal too much. We need to make sure that we adjust our microphone gain or what is called the transmit audio properly so that our ALC will operate properly, and it will be, we are doing SSB operations so that our SSB signal will be optimal. There's another setting as well that amateur radio operators will, or another feature rather, or that amateur radio operators tend to use on modern transceivers. It's called VOX operation, VOX. And VOX is simply voice operated control. So instead of using a push to talk or pressing a switch or PTT, instead of pressing the microphone, it's a sort of hands-free operation. So what happens, instead of us pressing the push to talk and then start to talk, and then when we finish speaking, we release the push to talk, we speak, and the radio will key up the transmitter on the basis of us just speaking. So that is why we call it hands-free operation or VOX operations, right? Voice operated control, that's what VOX means, as opposed to PTT or push to talk operation. So voice operated control of VOX is the radio will listen to our voice through the microphone and then start to transmit once it hears it. Of course, we need to make sure that the environment is fairly quiet and no other persons are nearby talking. Otherwise, when they speak, it will cause the transmitter to go into transmit mode if we are using VOX operations. Right? So we have an exam question around that as well, which is voice operated control or VOX versus PTT or push-to-talk operation allows for hands-free operation. And what that does, it frees the operator to do other things like log contact. So while you're talking and you're, let's say, in a contest and you have to log your operation, you can use your hands to write down or use a keyboard to key in the contact, the name of the person or the call sign of the person, the frequency of operations, the time of the contact, the mode of the contact, and so on. You could be writing that down or typing it on a keyboard with your fingers, so you don't have to press the push to talk. Some operators will use a foot switch as well to do that. And some are very comfortable using Vox operation, which is using your voice. It can take a little getting used to, but for the exam, you need to know about Vox operation, which is voice operated control. So just quickly, we have two exam questions that have been withdrawn. All right. Just note that we haven't come to them as yet. So we can now quickly go to our question pool review. All right. Let's switch quickly to our no nonsense guide and see if we can speed through these questions for all of the theory that we dealt with this evening, right? So again, we are running a little over time, folks, so thank you for the extra time. Okay, so first question, what could be a symptom caused by a ground loop in your station's audio connection? So we dealt with that and we said that a symptom of a ground loop is a hum. So you receive reports of hum on your station's transmitted signal. So the other amateur radio operator that is listening to your transmission will say you have a hum in your signal. And that could be because of a ground loop. How can the effects of ground loops be minimized? We said that to do that, we need to bond all of our equipment together, the enclosure, and that's the answer. Bond equipment enclosures together. What is a possible effect of a resonant ground connection? If we have a resonant ground connection, high RF voltages on the enclosure of the station equipment could be the result, which is not a good thing. What is a possible cause of high voltages that produce RF burns? Well, if it is that our ground wire has a high impedance for the frequency that's being used, that could cause that high voltage in the shack. So the answer is the ground wire has a high impedance on that frequency. Why must all metal enclosures of station equipment be grounded? The reason we must do that is because it ensures that hazardous voltages cannot appear on the chassis. That could be dangerous for you as a ham radio operator. You touch the equipment and you get a shock. All right, what technique helps to minimize RF hotspots in an amateur radio station? So RF hotspots mean that you can get an RF burn, right? So to avoid that, you bond all your equipment enclosures together. And we show the technique of doing so in the diagram. Which of the following could be a cause of interference covering a wide range of frequencies? Well, we show that an electrical pole, if you have a poor connection and it causes arcing, arcing at a poor electrical connection could be the cause of interference where you have wideband interference across a large section of the spectrum. You switch bands, any frequency you go to, you're getting wideband noise, and that could be caused by arcing due to poor electrical connections. What is the purpose of a speech processor in a transceiver? So we did say when we turn that on, that will help to increase the apparent loudness of the transmitted voice signals. How does a speech processor affect the single sideband phone signal? It does it by it increases the average power. What is the effect of an incorrectly adjusted speech processor? Well, we said that all of the answers in the question would be correct. You can get distorted speech, you can have excessive intermod products, and you can have excessive background noise. Things that in the background, like a dog, for example, will sound loud, very, very loud. It might even overshadow the voice. Next question up in the question pool, what does an S meter measure? So we said it measures received signal strength. Next question up, how much change in signal strength is typically represented by 1 S unit? So we said 1 S unit is 6 decibels or 6 dB. Next question up, how much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? So let's dissect this question. What are they asking us? How much must the power output of a transmitter be raised? In other words, they're saying how much to increase the transmitter power. They will be asking us how many times. But to do what? To change the S meter reading on a distant receiver. So in other words, not our S meter where we are, but our colleague, the other amateur radio operator, he or she has an S meter on their receiver. And we want to change that. We want to increase our own transmit power so that our colleague on the other end of the globe, perhaps, the signal goes from S8 to S9. How much must we increase our transmitter power to achieve that one S unit increase on the receiver end? And the answer for one S unit, it's approximately 4 times the transmit power we must use. How does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? So we did say to go from S9 to 20 dB over S9, it is a 100 times increase in power. Next question up, how close to the lower edge of a band, I say again, how close to the lower edge of a band's phone segment should your displayed carrier frequency be when using 3 kHz wide LSB? So let's dissect this question. What are they asking us here? So they're talking about the band's phone segment. So remember, there's a band plan. Part of the spectrum that we are licensed for will go from one frequency to another, but then even within that band, we can use some of it for digital mode, some of it for voice or phone mode, and there's the upper end and the lower end of that phone segment, right? So we need to know that if we are using lower sideband, the occupation, the bandwidth is 3 kHz wide. So if we are doing lower sideband, we cannot tune our radio to the lower end of the exact lower end of the band edge and then switch to lower sideband. That will cause us to be outside of the band segment. So what we must make sure is that whatever we are punching into our radio is at least 3 kHz above the bottom edge of the segment. Right? That's what that question is asking us. Next question up. So relatedly, what frequency range is occupied by a 3 kHz lower sideband signal when the displayed carrier frequency is set to 7.178? So if we punch in 7.178 into our radio and we switch to lower sideband, that lower sideband signal occupies 3 kHz. So we have to minus 3 kHz from 7.178, and that takes us to 7.175. And therefore, the occupation of that, or the frequency range that it occupies, will be from 7.175 to 7.178. That is the 3 kHz bandwidth occupation of the lower sideband signal. All right, so we go into the upper side now. How close to the upper edge of a band's phone segment should your displayed carrier frequency be when using a 3 kHz wide USB? So let's dissect this question a little bit. What are they asking us? So we are punching in our frequency, displayed carrier frequency on our radio, but we are using upper sideband USB. And they want to know how close to the upper end could we actually punch that in? Well, we cannot punch in the upper end. We have to go at least 3 kHz below the end of the edge of the band. And we say at least 3. I would go a little more just to be safe, right? So you cannot go at the upper end. You have to go 3 kHz below because our upper sideband signal will occupy 3 kHz. All right, so hopefully the mathing there, right? All right, next question up. What frequency range is occupied by a 3 kHz upper sideband signal with the displayed carrier frequency that is set to 14.347? So if we punch 14.347 into our radio and we switch the mode to upper sideband, they want to know what is the bandwidth that will be occupied, right? Well, we're punching in 14.347, so it starts there, but we put in upper sideband, so it's going to occupy 3 kHz above. So 14.347 plus 3 kHz is 14.350. So that's the range, 14.347 to 14.350. That's the occupation of the bandwidth occupation or the frequency range for an upper sideband signal. All right, some more questions. Which of the following direct fuse power connection would be the best for 100 watt HF mobile installation? What are they asking us? So we are installing a 100 watt radio, a HF radio into our vehicle. What's the best way to get power? The answer is to use the battery using a heavy gauge wire. Next question in the question pool. Why should DC power for a 100 watt HF transceiver not be supplied by a vehicle's auxiliary power socket? Again, think of that as the cigarette lighter adapter. Why would we not want to use that for a 100 watt fairly high power transceiver? It is because the socket's wiring may be inadequate for the current drawn by the transceiver. And you can melt the socket, you could have overload, you can do all sorts of things there that will not be desirable. Next question in the question pool. Which of the following may cause receive interference to an HF transceiver installed in a vehicle? So first of all, the battery charging system could cause the interference, the fuel delivery system could also cause receive interference, and the control computer or the brain box could also cause, that circuitry could cause receive interference. Therefore, all of these choices are correct. Next up, which of the following most limits an HF mobile installation? So the main limit when you go mobile HF is the efficiency of the electrically short antenna. Remember, it cannot be as long as a base station antenna, and HF frequencies require long antennas. So that is your main limitation, the length of the antenna and the efficiency associated with it. What? Next question. What is one disadvantage of using a shortened mobile antenna as opposed to a full size antenna? Let's dissect this question. What are they asking us? They're asking us for a disadvantage of what? Using a shortened mobile antenna. As opposed to what? As opposed to a full-size antenna. That full-size antenna, for example, may be a base station antenna. So when we go with a mobile antenna that has to be smaller because it's a car or vehicle we're installing it in, what is a disadvantage? Well, because we are using that short mobile antenna, the operating bandwidth may be limited, right? Next question. What is the purpose of a capacitance hat on a mobile antenna? So we showed visually what a capacitance hat may look like. But what's the purpose of it? The purpose is it's a mobile antenna, and therefore it is to electrically lengthen a physically short antenna. That is how we generate or we create or we design mobile antennas. It is physically short, but because we use techniques such as capacitance hats, it will make it seem longer for radio frequency purposes. Next question, what is the purpose of a corona ball on an HF mobile antenna? So we also showed what that looked like at the tip of the antenna. What's the purpose of it? It is to reduce the RF or radio frequency voltage discharge from the tip of the antenna while you are transmitting. Okay. A couple more questions in the question pool. What is the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? Okay, so that's a mouthful. Let's dissect this question. What are they asking us? They're asking us what is the approximate open circuit voltage. So we know the answer is going to be something volts. But from what? A fully illuminated, so that means the sun is shining, right? Silicon photovoltaic cell or PV cell, right? That is essentially a solar cell, which is what solar panels are made of. Right? So that solar cell, when it is fully illuminated by the sun or sun rays, will generate an open circuit voltage of approximately 0.5 volts DC or half of a volt DC. In what configuration are the individual cells in a solar panel connected together? So we did say that a solar panel is connected of multiple cells, and we have to connect them to be able to deliver the required voltage. And the way we connect them is cells are connected in series, yes, but those series connected cells are also connected in parallel. And when we do that, it's called a series parallel configuration. Okay, next up. Why should a series diode be connected between a solar panel and a storage battery that is being charged by the panel? Let's dissect this question. What are they asking us? Why should we use a series diode? Remember what a diode does? It allows the flow of electricity or current in one direction only and not the other, just like a check valve in the water circuit, right? Why must we use such between a solar panel that is charging a battery? Well, the reason is that when the sun goes down and there's no illumination of it, it prevents the discharge of the battery through the panel during times of low or no illumination, right? So that diode will prevent the battery from somehow trying to deliver power to the panel. Okay. What precaution should be taken when connecting a solar panel to a lithium iron phosphate battery? So we did say in such a case, we must use a charge controller. So the solar panel must have a charge controller. That's the answer. Okay, a few more questions. Right, so we're now into operating procedure questions. Which mode of voice communication is most commonly used on the HF amateur bands? So what are they asking us? Mode of voice operations. Is it AM? Is it FM? What mode? Is it PM, phase modulation? Commonly used on the HF band. So we did say SSB or single sideband is very commonly used by amateur radio operators on HF. Right, so remember to refer to that trusty diagram that we'll have at the end of the slide deck for what is HF, what is VHF, what is UHF, where we use lower sideband, where we use upper sideband, right? So that chart will come in handy until it is second nature to you. Next question in the question pool. Which of the following statements is true of single sideband or SSB? Only one sideband is transmitted. The other sideband and the carrier are suppressed. Remember, when we're generating a single sideband signal, it starts off as amplitude modulation. You have a carrier and you have the two sidebands. What you do is you filter, you suppress the carrier, and you filter or suppress the one sideband, so you're left with the other sideband. And that is what is transmitted. Right. Last couple of questions, folks. Thank you very much for staying with us. See, everybody's still with us. Really good commitment. We know it's late on a Friday. Let's continue. Which of the following is an advantage of using single sideband as compared to other analog voice modes on the HF amateur bands? So let's dissect this question. Which of the following is an advantage using SSB or single sideband as opposed to other analog voice modes such as AM on the HF amateur bands? In other words, we're looking for an advantage, main advantage of SSB. Well, using less bandwidth, and also we end up with a greater power efficiency. Okay, which mode is most commonly used for voice communications on frequencies on 14 megahertz and above? We said USB or upper sideband. Which mode is commonly used for voice communication on 17 and 12 meters? So those are actually above 14 megahertz. So the answer is also upper sideband or USB. Again, that trusty chart at the end of our slide deck will put all of that into context and you'll be able to refer to it until again it becomes second nature. Which mode is most commonly used for single sideband or SSB voice communications in the VHF and UHF bands? We said we typically use only upper sideband for VHF and UHF. Once we're doing SSB on the VHF spectrum and the UHF spectrum, those bands we use upper sideband only. That's conventional. All right. Which mode is most commonly used for voice communications on the 160, 75, and 40 meter bands? So those are the lower parts of the HF spectrum. We say anything below 7 megahertz and below will be lower sideband or LSB. Why do most amateur stations use lower sideband on the 160, 75, and 40 meter bands? The simple answer is just convention, right? So it is commonly accepted amateur practice. It's as simple as that. Okay, what control is typically adjusted for proper ALC, automatic level control setting on a single sideband transceiver? What control is typically adjusted for that? It is the microphone gain or the transmit audio setting. Very important, especially for SSB operations. You don't want to have it too high, you don't want to have it too low. Too low, you'll have lower power output. Too high, you may distort your transmission. Last question in the question pool. Which of the following statements is true of VOX operation versus PTT operations? Let's dissect this question. What are they asking us here? Which of the following statements is true of VOX operation right? Voice operating control, right? That is where we speak and the transmitter will operate. We're not pushing or pressing a push to talk button. We're not keying down physically. We may use our hands for other things like writing a log or typing a log or doing something else. So we are going to transmit when we speak. So the following statement is true. It allows us to do hands-free operation. Again, fairly straightforward, fairly simple point. Okay, Ramzan, yes, solar controllers regulate voltage. Very true. Excellent point there. All right, so folks, let's just quickly switch back to our slide deck. And just to mention, next week we'll talk a bit about it more again. Upcoming, there's a amateur radio convention. It's called Hamcation. That's coming up in the month of February. So what we will do is perhaps for the next session, we'll talk a little bit or put up a slide about Hamcation. It's going to be held in Orlando. So we'll share a bit about that information for the next session. So let's just go back to our slide deck. Right, so we have been covering pages 91 to 101 in our No Nonsense General Class License Study Guide for those of you who are following along. Right, so we come to our trustee table. This we'll be including this in all of the slide decks going forward. It's just a good handy reference. Tells you the various frequency bands that amateur radio operators are typically licensed for, depending on your class of license. It gives you the wavelength associated with the particular frequencies. It also tells us whether we use lower sideband or where we use upper sideband. So you'll see here that lower sideband is anything below here. Upper sideband is anything above here, right? So hopefully that visually will help you understand or reference. You can see it, what HF is, what VHF is, what UHF is, and so on. Okay? So hopefully this is helpful as a reference. We encourage you to take a look at this as often as you can. If you have a hard time remembering where to use lower sideband, where to use upper sideband, and what are the various pieces of spectrum that we have access to as amateur radio operators. So folks, again, if you have any questions, feel free. I think we dealt with all of the questions that were asked this evening. Ran a little over time, answering some of the questions too. Feel free to send an email to this email address on your screen, as well as this number is good for WhatsApp. You can WhatsApp any questions that you have. We do have a WhatsApp group for anyone that's now joining. Feel free to join this WhatsApp channel. You will get announcements not only about this course, but other relevant information, hopefully, that you'll find interesting. Feel free to join. The next session will be scheduled for next week, Friday, the 2nd of February, 2024, at the usual start time, 8:30 p.m. So folks, thank you so very much for staying the course. Thank you for the extra time. We have gone really over time this evening. I think this is one of the latest sessions that we have run, and I see everyone has stuck with it. No one left, and we really do appreciate that. And we will see you next week. So until then, everyone, do have a great weekend, a great week ahead. Be safe and take good care. Have a good night.